So what happens when a massive asteroid is hurtling through space on a collision course? Not with us, but with the moon. Now, this isn't some sci-fi movie plot. It's a very real scenario that planetary defense experts are keeping a close eye on right now. Let's get into what's actually at stake.
Mark your calendars for December 22, 2032. That's the day we could see the largest lunar impact in all of recorded history. But this is way more than just a spectacular light show for astronomers. An impact on the moon could have some very real and honestly pretty surprising consequences for all of us back here on Earth.
The object we're talking about is an asteroid about 60 meters across. Now, to give you some perspective, that's roughly the size of the Leaning Tower of Pisa. It's in the same ballpark as the asteroid that caused the famous Tunguska event back in 1908. Point is, it's big enough to make a serious impact.
Now, I know what you're thinking. A 4.3% chance of hitting the moon? That doesn't sound like a lot, right? But in the world of planetary defense, odds like that are taken very seriously. That number is way above the normal threshold that makes scientists sit up and pay attention.
So, here's the key takeaway. Earth is safe from a direct hit. Phew. But our closest celestial neighbor? Not so much. So let's meet the main character in our story, Asteroid 2024 YR4. The rock that's making us completely rethink what planetary defense even means.
The story of 2024 YR4 really starts like a lot of these do, with a totally routine discovery that, well, very quickly became anything but.
Okay, so it was first spotted in late 2024, and for a couple of pretty tense months, it looked like it might actually be headed for Earth. By February of 2025, that was ruled out. Big sigh of relief, right? But just as Earth's risk dropped to zero, the moon started to climb, eventually landing at that 4.3% figure. The problem is, we won't get a better look until 2028 when it swings back into view, which leaves us in this weird state of suspense until just a few years before the potential impact in 2032. So you can imagine everyone breathed this huge sigh of relief when Earth was declared safe. But that feeling didn't last long, because scientists quickly realized that an impact on the moon, well, that presents an entirely new and complicated kind of challenge.
And this is where we get to a fascinating dilemma. On the one hand, this impact is a serious, serious danger. It could blast 100 million kilograms of moon rock into space, creating a super dense debris field that threatens our entire satellite network. But on the other hand, for scientists, this is a historic opportunity. It's a massive natural experiment that could carve out a kilometer-wide crater and trigger a huge moonquake, giving us an unbelievable look deep inside the moon's core.
Let's just try to wrap our heads around that number. 100 million kilograms of material, known as ejecta. That's about the weight of a modern aircraft carrier, just blasted into space at escape velocity.
And hidden within that incredible mass, scientists think there could be a staggering 100 trillion particles larger than 100 micrometers. And that's the critical size where a tiny piece of debris can cause catastrophic, mission-ending damage to a spacecraft.
And look, this isn't just a problem for a few science satellites. We're talking about the very backbone of our modern world. Your GPS, global communications, weather forecasting, all of it could be at risk from this sudden, massive cloud of space junk. It would be like getting years' worth of debris exposure in just a matter of days.
Okay, but now let's flip the coin and look at the incredible scientific upside. For researchers, this impact would basically be like giving the moon a giant CAT scan. The shock waves from the collision would ripple through its interior, telling us all about its core, its mantle, and its crust in a way we've just never been able to see before. This impact would create a massive moonquake. Now, looking at this chart, you can see that the most powerful quakes, these shallow quakes, are also the most rare. They're only about 5% of all the seismic activity on the moon. An event of this magnitude, a 5.1, would be one of the strongest we've ever recorded. By studying those waves, we could finally answer some huge questions, like does the moon have a solid or a molten core? What's its deep mantle made of? It's a once-in-a-lifetime chance to really understand how the moon was born and how it evolved. So, faced with this totally unique threat, part danger, part discovery, the question is, what can we actually do about it? And this is where we open up the planetary defense playbook.
The first thought might be to just, nudge it out of the way, kind of like what NASA's DART mission did. But in this specific case, that's actually way too risky. We just don't know enough about the asteroid's exact mass or what it's made of. A nudge that's too weak won't do anything, but a nudge that's too strong could shatter it, creating a whole new cloud of fragments we can't track. There's just not enough time to figure it all out and then build the right spacecraft for the job.
So that leads us to a much more aggressive strategy called robust disruption. Instead of a gentle nudge, the goal here is to hit the asteroid so hard that it's completely pulverized into tiny, widely scattered fragments. You want to make sure the debris cloud is so spread out that it poses almost no threat to the moon or to us.
And there are two main ways to do that. The first is a kinetic impactor, but think of it as DART on steroids. Much bigger, much faster, and designed for maximum destruction. The second option is a nuclear explosive device. Now, this wouldn't be a direct hit. It's what's called a standoff detonation. It would explode a short distance from the asteroid, instantly vaporizing the surface and blowing the whole thing apart with just overwhelming force.
So this table kind of lays out the potential game plans. You'll notice they all start with reconnaissance missions to get a better look at our target. Option 1 is the simplest, a quick flyby, then send in the kinetic impactor. Option 2 is a bit more involved, adding a second spacecraft to hang around and watch the fireworks. And Option 3 involves a rendezvous mission that would actually deliver a nuclear device. But look at those launch windows. They are tight. We'd have to make some big decisions very, very soon.
So with the stakes this high and these incredible options on the table, what does the road ahead actually look like?
The timeline from here on out is absolutely critical. In 2026, we're hoping the James Webb Telescope can get an early peek to help nail down its orbit. But the real moment of truth, that comes in 2028, when telescopes on the ground can finally see it again. That's when we'll probably know for sure if it's going to hit. And if the answer is yes, then the launch window for any kind of mission opens up immediately after that. It is a real race against the clock.
In the end, whether 2024 YR hits the moon or not, it's a powerful reminder of a fundamental truth. The Earth-Moon system, it's a dynamic place. It's like we live in a cosmic shooting gallery. Impacts on the moon have been flinging bits and pieces at Earth for billions of years. This event just brings that constant cosmic exchange into sharp focus for us, a civilization that now depends on space.
And this all leaves us with a huge question, one that's captured perfectly in this quote from one of the key research papers. The whole situation with 2024 YR4 forces us to ask, is it really enough to just protect our own planet? Or does true planetary defense in the 21st century mean we have to start protecting our entire cosmic neighborhood?